So worksheet 3, we're going to be really talking about capacitors, right? So we kind of gone into detail about this before, but let's just establish some background. A capacitor consists of two conductors electrically isolated from each other and their surroundings. Very important to remember is these capacitors store charge in the form of an electric field. So it's not dissimilar to a battery. Oftentimes people are like, oh, what really is a capacitor? It's almost a battery that is charged, right? So that's why when you can disconnect it, some things change, and when it is connected, it like charges up. And there's two methods of calculating capacitance, and I provide both of them here. The only thing, Q is that charge stored in units of coulombs, V is that voltage across the capacitor, C is the capacitance of the capacitor. And then looking down here, we have this other expression where K is the relative permittivity, and that's just equal to 1 in the vacuum and air. And there's no other way we solve it without it equaling 1. So you can almost imagine it's not there, multiplying by 1, right? And then that E naught is the permittivity of free space, and that's just a constant that you'll be provided. And then S is the surface area of one plate, and D is the distance between them. We actually don't use this equation that much, but it's kind of important to know where it comes from. And actually, speaking of equations, has he posted the equation sheet yet? I haven't seen it. No. So as soon as he does post that, incorporate that into your studying and homework solving, because you're going to get the same one on the exam, and you want to be very familiar where things are on that thing, because you don't want to be like during the exam for the first time looking for an equation. Okay. And then for solving for equivalent capacitance of parallel plate combinations, we can see that when they're in parallel, you just add them, right? And alternatively, when they're in series, you do this inverse addition. This right here is a quick way to do inverse addition when you're only working with two capacitors. So if you have two, you can solve like this, with C1 and C2. Those are the two capacitors. Any more than two, you have to use this methodology. And then capacitors in series have the same charge. And what is series? That's a circuit element that is not separated by junction. Then capacitors in parallel have the same voltage. And the ones that are in parallel have a junction in the loop. Okay, so here in the notes section, I think it might be a good idea to just write down a few things. First is certain qualities remain constant when a capacitor is connected to a battery or not. So when it is connected to the battery, the voltage is constant. So connected to battery, constant voltage. Disconnected from the battery, the charge remains constant. And I think that's where a lot of confusion related to number 4 stems from. And I sent an email to summarize number 4 fairly well. Well, I shouldn't say that about myself. It was good. It should make it clear for you guys. Okay.
So you said disconnected from the battery, what?
Charge remains constant. Okay. So truthfully, with capacitors, first is I don't guarantee things often, but I'm almost guaranteeing this kind of question will be on an exam where you have like some capacitor and you need to work it out, right? And the other thing is there's only a few ways these questions come. So we're gonna have two questions where we practice the main way, and then one that's gonna be a little bit different just to keep everyone thinking. So let me post question 1 here into this iPad. I don't know why it's not showing anything. Oh, wow, it's just very slow, that's why. Okay, one second. All right, so I'm gonna pause the recording and see if maybe I can make this faster because this delay is ridiculous. Okay, so now this should be a little easier for everyone to see or in recording. So here we want to determine the equivalent capacitance for the system of capacitors as shown in the figure. We're given the capacitance of each capacitor, and then we want to determine the charge on each of the capacitors. So I kind of said this during the homework review. Whenever I start these kind of problems, I like to work furthest away from the battery. So that position in this question would be these two capacitors. Now, what's the relationship of these two? Right, series. So with capacitors in series, we know we just do that inverse addition. So the quick ways we're going to do now is going to be that I'm going to call it, what do I call it here? CS is equal to 16 times 32 divided by 16 plus 32. that CS comes out to be equal to 10.7. Okay, and I like to put it in quotes. Microfarads, right? And then if we redraw this, okay, and up here, I'm going to do this 10.7. Down here we have C3, here at 200. What do we have here? Two capacitors in parallel. And that's because, actually I like to do box for parallel. In parallel. And that's because we have this junction right here, like this, right? Effectively, the current has two ways it can go. It can go like that or like that. That's how I know it's a junction. And with parallel, we just got to add them up. So nice and simple. So we'll say that's equal to CP, which is equal to 10.7 plus 8. Oh, I'm sorry. Oh, wait, that was 8. Plus 8. Therefore, CP is equal to 18.7. Okay. And then we redraw it one more time. Oh, actually, well, I'll just draw it just for sake of working through this guy. We have that 18.7, and this is our 200. Okay. And therefore, our equivalent capacitances, we simplify this as far as we can go. CEQ is equal to that 18.7. Okay. Now, what's the charge on each capacitor? Well, right off the bat, we're going to be able to solve for the charge. Well, let me see this real quick. All right, so to solve for Q3, that's where we're going to start, right? For Q3, which is, in series with the battery there, we can say that Q3 is equal to CEQ. No. Is equal to C3 times the total voltage, right? No, I'm sorry, I misspoke. Here. Okay, yeah. Times C3 is right. And that C3 is equal to 8 times 24. And that whole thing comes out to be 172 microcoulombs. And the kind of the harder one here is with those two that were previous. Well, they're in series, so we know the charge of them is equal to the same. So we'll say Q1 is equal to Q2, but we don't know what that's equal to yet. So to find that, we're going to first need to work a little bit backwards. We need to.
I have a quick question.
Uh-huh.
Where did you get the 24 from for the? Isn't it a 200-volt battery?
Oh, sorry. It's actually 24. Sorry, I wrote it wrong. I think I wrote it wrong on the key too.
Yeah. So it's supposed to be. Oh.
Yeah, this is supposed to be 24. Sorry. Thanks. I didn't even notice that. So yeah, make sure you change that to 24 there. This guy. Okay. So we don't know what those two are equal to, but we do know the voltage drop across this guy right here. Right? It's equal to 24. So as two that are in parallel, we know that they're also made up of that 24. So working all the way backwards, now all we need to do is multiply that capacitance value, that C1 and 2, times 24. So this whole thing is equal to 18.7 times 24, which equals 256 microcoulomb. Okay. So let me pause the recording real quick. Oh, shoot. That's not 18.7. That is 10.7. That's this value right here. 10.7. Sorry. It's the capacitance of the two that were in series. So yeah, sorry about that. Okay, pause the recording. So for question 2, the first two, C1 and 2 are in series. And then drawing it out again. Be something like this. Okay. Let me just rewrite, and then we'll do next step. Okay. So how about now? This is where it gets a little tricky. Any suggestions? Yes, very good. That's where exactly I would look to. With the ones that have the diagonal, you really want to knock out that diagonal as quick as you can, just because it clears up everything greatly. So those two are in parallel. So what we have to do is just add them, right? So CP is equal to 8 plus 4 over 3. This comes out to be equal to 28 over 3.
Why are they in parallel?
Because there's a junction between them, right? The current has two choices of which way it can go. It can go this way or it can go this way. So these right here are junctions where the blue is.
That makes C5 also in parallel then, technically speaking. Since it can run in 3 ways.
I wouldn't do with the diagonal, just try to do one and another one, right? Because we're going to see what's going to happen with that C5 in a second. Okay, so to just redraw it, I'm just going to do this. This. And now at that position, we have that 28 over 3. All right. So now, where do we think is another good one to do?
The 28 over 33 and 60 are in series.
Yeah, zoom back. Okay, so you said between the 28 over 3 and?
Yeah, 28 over 3 and those C3 are in series.
Correct. So those two are in series. Okay, so with series, we just do that inverse addition again. That 28 over 3 times 1. And then that's 28 over 3 plus 1. Okay, and from that, we get it's equal to, sorry, I'm making this very messy. Okay. CS is equal to 28 over 31. Redraw again. Sorry, my drawings are a little crude here. Like this. 28 over 31. Okay. And now we can do the last step and address those final two positions, which are in parallel. And why are they in parallel?
Hannah?
Hannah. Oh, that's Hannah. Where is the junction?
Oh, wait,
Say-
it's not the-
We're talking about this one right here.
Yeah, is it not parallel?
No, okay, parallel's right. So where's the junction? Say to the left or right of where?
They're on both. unfortunately.
Yeah, there are. So on the left and the right of C5.
Yeah, okay.
Right, exactly.
Sorry. Oh.
No, you're good. Yeah, junctions on the left, and this stuff becomes very important, especially into Kirchhoff's law, which is a guaranteed exam question. And there it becomes a little bit more complicated because we also have resistors. So it's good to kind of get comfortable at identifying the junction. You're going to get a lot of practice doing that. Okay, so in parallel, we just get to add, and that's what we're going to do here. And, we solve for now the equivalent capacitance. You just add them. CEQ is equal to 3.9. Okay, so part A done. CEQ is equal to 3.9. But that's not why we're doing this question, to solve for the equivalent capacitance. At this point, I would say, like, it's good to expect of yourself to be able to solve for equivalent capacitance with ease. Working for the charge is a little bit more difficult. So let's do that. And I want you guys to drive this thing. So we need to find 5 charges, right? So for part B, we need to find Q1, Q2, Q3, Q4, and Q5, right? We don't know what any of those guys are equal to. So what's the first step? Always the first step. Yeah, the total charge. So the QEQ, as I like to call it. QEQ is equal to CEQ times the total charge of the battery, right? So that's just equal to 3.9 times 12. QEQ is equal to 46.8 microcoulomb. Okay, double underline that. That guy is important. So what we could do next is solve. So we know the charge here, right? I'm going to do that in orange. So QEQ is equal. I'm just going to write QEQ. We know it. We already wrote what it equals to. Okay, so good. We found QEQ, but what's next?
The voltage is going to be the same across the parallels. So
Okay.
28.30.
Okay, so so which one do we solve for? Oh, sorry, you tell me.
We can solve for C5.
C5. Okay, exactly. So what's C5 equal to? Or I'm gonna say Q5 is equal to what? Well, what's the equation? Q equals what?
Q is equal to Q5 is equal to C5 times 2.
Okay, so C5 is equal to, what's that, 3 times 12, right? Those that are in parallel have the same voltage drop across them. So here it's that 12, and here, wait a minute, it's that 12 also. Okay, so that's how we know. In parallel, they're the same. That comes out to be Q5 equals 36 microcoulomb. All right, nice, one down. So next, we can use what we know, because we now know the voltage drop at this position, and we know which capacitors, that being these two, make up this position. So now we can solve for C3. So using what we know, so that's that Q equals that C, where that C is that 28/36 times V at that position, which is 12 for the reasons we discussed. Q is equal to 10.84. That's not for that's not for C3 though, right? That's the charge of this position. But now we can look at these two, which are in series. And because they're in series, therefore they have the same charge. So that's the logic you have to use here. So therefore, Q3 is equal to 10.84 microcoulombs. Was that clear to everybody? Kind of that jump I made? People on Zoom too? Can't even tell if the people on Zoom are talking.
Wait, so just first we found the charge for
Okay, so let me explain again. Someone on Zoom asked too. Okay, so we know the capacitance here, right? That's that 28 over 36 there. I'm sorry, over 31. Over 31. And we know what the voltage drop is here. So we can solve for the charge that's here. That charge, 10.84, makes up, that charge, 10.84, belongs to a capacitor, made up of these two which are in series. By definition of capacitors in series, they have the same charge. And that's how we get that value. Yep. Okay. So we also know now the charge here. Again, they're in series. So we can use the charge here to work to find C4. So that means C4 is next to be solved. But to solve for C4, we're going to need some comment on voltage. So we can say that Q3 is equal to that C28, the capacitance, where it's 28 over 3 times this V, let's call it V prime. But we don't know V prime. We know Q3, we already solved for Q3, but we don't know that V prime. So we have to rearrange the equation. So we're going to have 10.84 divided by 28 over 3 is equal to V prime. V prime is equal to 1.16 volts. Okay. So now we have information regarding these two capacitors right here. We know voltage drops like this. Call that V prime and V prime. Knowing V prime, we can solve for Q4, right? We know the capacitance here. We know the voltage there. Q equals CV. So Q4 is equal to C4 times that V prime. Q4 is equal to, that's 8 times 1.16, which is equal to 9.3 microcoulombs. Now we have Q3 and Q4. So bam and bam. Any questions? All right, almost there now. So we solve for Q4. We know that what the voltage drop here is. And we know that this position is the result of a condensed two capacitors. So if we find the charge here, we find the charge of C1 and C2. Works out pretty nicely that way. So what we got to do is plug in to solve for that value. So I'm going to call it Q, and I'm just going to say 4 over 3, because this isn't Q1 or Q2. This is the charge of this position here, which coincidentally is these two charges. So that is equal to Q. We know what the C value is here, right? So that's that 4 over 3 times that V1 we just saw for 1.16. Q3 over 4, I'm sorry, 4 over 3 is equal to Q1, which is equal to Q2, which is equal to 1.55 microcoulomb. And bam, we've now solved for the charge at each capacitor. Okay, let me just take a zoom out here. So this is kind of more the level I would say you should expect for an exam type question of this type. It's very important that, I mean, if you're comfortable skipping steps, obviously, you know, it's your choice to do what you want, but I recommend like doing a nice and easy here, right? It won't hurt. Just do 2 at a time, clean it up, go step by step, show all your work, and then solve for your equivalent capacitance, and then work all the way backwards, okay? And a way you can check this value is, you know, once you get your QEQ, you should know that QEQ divided by CEQ is equal to V, and V is given. So that's a way you can kind of do a quick check. Because if that equivalent capacitance is wrong, you're gonna have a bad time for the rest of the question, you know? So it's a quick check. Any questions on this? I'd say it's very important that this is something that we feel very comfortable with. Let me check Zoom chat. Okay, cool. Nice. And this is another question that was on one of the midterms, probably from 2019, I want to say. And another time it came up. Truthfully, not that hard. And rather, it's a little annoying, honestly, just because it takes a lot of time. It was very similar. Yeah, but I mean, like, you know, things change. And I think that this one's is good to show the map, like the process behind it, because I would say this has been asked, but it's just multiple orientations where just some things are shifted around. So wouldn't be bad practice. Okay. So we're told the charges at these 3 positions. And we're asked to find the electric potential at point A. And then we want to determine the electric work done by the electric field at point B. So in part A, everyone always gets kind of it's tricky with the wording, right? What's this electric potential, potential difference, voltage? It's effectively the same thing. What we're solving for is the voltage at A. We don't know what that's equal to. And what contributes to it is each charge is going to contribute to it, right? So we can say VA is equal to the sum of all of them. So V1 plus V2 plus V3. What's the equation here? That's that K Q1 over R1 plus K Q2 over R2 plus K, Q3 over R3. Okay. You can factor out K, do what you will. Kind of the part that makes this question a little bit, I don't know, a little bit tricky is that you just need to do a lot of just like Pythag to solve, right? So you just have to draw a few triangles. Like this. Okay. So we know from here to here, it's 2. Oh, I remember why this one's tricky. Because like the way the diagram is, it's both at x-axis equal to 4, but it looks like this one's slightly to the left. I remember that messed me up when I was practicing this one. And the distance from here to here is 0, right? There's nothing actually there. It's 6 vertically in the air. And from here to here, it's equal to 1. And I'll do it in blue, from here to here is equal to 2. Okay. So I'll leave doing the Pythag to you guys, but I'll just say this. R1 is equal to 6.3. R2 is equal to 6. These are all in meters. And R3 is equal to 4.12 meters. This. And at this point, it's just simple, plug everything in and solve. Okay. And the answer to that is 470.18 volts VA. Okay. So now we need to solve for this work done by the electric field at point B. This is a little bit more tricky. Does anybody remember the equation that we're going to be using here? This is going to be the work by the electric field. It's going to be equal to Q and that change in potential, right? Change in potential times the charge. That's the work equation. And by definition, that delta Q is going to be equal to that V final position, B, minus the initial position. So A. We already solved for VA. Now we just need to solve for VB. And we do that in a very similar way. VB is equal to V1 plus V2 plus V3. The only difference now is our triangle has kind of reoriented, right? So using the same logic as before, I'll let you guys do that just for the practice. I guess I can tell you what, so R1, I'll tell you what they're equal to, but I'll let you guys just do it for the practice, for those who need practice their trig. R1 prime is equal to 8.94 meters. R2 prime is equal to 8.25 meters. And R3 prime is equal to 6.71. Okay. And then, business as always. Oh, that comes out to be equal to minus 2.22 V. And remember, this is a scalar value too. So that Q2, which is negative, you plug in the negative, right? Plug in the negative. So it'd be like minus 4 times 10 to the minus 6. So now you have VB, VA, what the charge is, which is that's minus 6 times 10 to the minus 6. So you can now solve for Q4. Oh, did I not tell you guys what Q4 is? So there's a minus 6 microcoulomb charge here. at Q4. So then Q4 is equal to that minus 2.22 minus 470 times 470.18. And this whole thing is equal to 0.0028. What are the units of work? Yeah, exactly. Yep. Any questions on this one? People on Zoom? All right, pause the recording.